Okay, today we will talk about several real-world examples of buffer overflow and other approaches we can use to find those vulnerabilities and exploit those vulnerabilities. But today's class will be a little bit high level because especially for the part of finding vulnerabilities and automatically exploit vulnerabilities, I plan to offer another class next semester, the seminar class. It's just dedicated for that. We will spend the whole semester on fuzzing, symbolic execution in that. That will be a seminar class. So if you are interested, you can, since you guys take this one, so I hope you can take the next one as well. So we'll look at several examples. The very first example, real world buffer overflow example is infamous Morris worm. So when we started talking about buffer overflow, I mentioned about this. So this happened in the late 80s. So Robert Morris was a graduate student from Cornell at that time. And he wrote the very first worm. And that worm took over maybe 80% of the internet by then. That time, maybe the internet has like around 1,000, 2,000 computers. So most of them was infected. This is exactly the vulnerability of this. I went back to the BSD Linux system and find the source code here and find the vulnerable code here. So the vulnerability is in the finger D program. D means daemon. So this is just a server program listening ports and getting requests from the internet. And as you can see that this program uses gets line. Okay, and that's a vulnerability, right? The same as the vulnerability you have been exploiting in this class, just the gets. And this gets will lead to the overwritten of those local variables and the return address of the main function. And because of that, the exploit can run arbitrary code. And back in 1980s, there is no stack array, there is no address-based layout randomization, there is no, what is the other approach we talked about? Non-executable stack, right? None of those defenses existed back then, okay? This worm actually has other weapons. It also exploits other vulnerabilities, but we haven't discussed that yet. But here you can see this is a real world thing. So what you are learning actually is a reflection of real world production system. Another example is in 2000, buffer overflow was discovered in this piece of code in FTP daemon included in the open BSD distribution. So this vulnerability is not as obvious as the ones we studied in the class. Okay. So this piece of code doesn't use string copy, string cat, gets, fgets, memory copy, those vulnerable functions. Okay, it's just the basic C operations. It's just a for loop. Okay. However, there is still a vulnerability. There is a off by one vulnerability. Off by one means you are overwriting one more byte than you should do. Okay, off by one, or you are sometimes overreading one more byte than you should do. The vulnerability actually is here, the plus plus I. If you are familiar with C, plus plus I will increase the value, the content of I first, then use that value to as the index to dereference this array. Okay. And because of that, so the array here actually is 1024 bytes. And because of that, you can overwrite 1 byte more. You can overwrite 1025 bytes. Okay. And that 1 byte will be the least significant byte of the saved EBP. Okay. So now you can overwrite saved EBP, but you can overwrite over only 1 byte. But still, it's a vulnerability. It's harder to exploit, but it is exploitable. So I want to show you this example because not only if you say string copy, memory copy, there will be a vulnerability. Even if no, some very complex for loops with array operations sometimes will also have vulnerabilities. And this is very hard to identify. Okay. But just by reading this, it's very hard to identify the vulnerability here. That's why we need some automatic approaches to identify those vulnerabilities. And that's what we will cover in my next semester's class. One more example. This is a very recent example and very interesting. And I think the hackers took away a lot of money by demonstrating this vulnerability through the 0-day initiative. There is an organization called 0-day initiative. You can present your vulnerability to them, present your exploit as well. There are other organizations, they will take your exploit. I think Linux Foundation also do that. You find Linux kernel vulnerabilities, present them, they will pay you. Google also have programs like that. So there is a recent event. I think this is multiple events. It's called a Pwn to Own events, and this one focuses on automobile systems. So if you hack anything related to automobile, like you hack a Tesla, you hack their infotainment system, you hack, in this case, these hackers hacked the EV charging station. Okay, the station, and so it's a big box like this. It has apps. So you have the app talk to the charging station through Bluetooth and also Wi-Fi, all kinds of wireless connections. And obviously, the app is developed in software. It's for Android, it's Java. If it's Apple, it's Objective-C. Then the juice box, the charging station, is basically an embedded system, right? It may run a Linux. It may have other bare metal systems running, and also there could be other operating systems. In this case, they're running this Gecko OS. And what the hackers find is they were able to dump the firmware of this charging station. Then they do binary analysis. They find the vulnerability. So this is the vulnerable piece of code. They didn't have the source code, right? They only have the binary code. The things like what you are doing in the class, you open it up. They find this piece of code. What this piece of code is doing is to expand kind of like a format string, and that format string will have it's a timestamp. There is a @t stands for expand this to the current timestamp. Okay, so @t is only 2 bytes, a @ symbol and a letter T. But when it is expanded to timestamp, it's much longer. It's like 13 bytes. And because of that, the buffer, so this is the piece of code to expand that format string and put that in the buffer somewhere here. I think it's a formatted message buffer. but the buffer is only 192 bytes. And because of that, you are overwriting to this buffer. But what you're overwriting is much larger than this. It could be as large as 200 or 300 bytes. Let's say they can overwrite 345 bytes, but the buffer is only 192 bytes. And because of that, you can overwrite the return address or other things. I'm not sure what hardware architecture this box is, but usually there is a return address. And this is more like an embedded system. There is no ASLR, there is no stack query, there is no non-executable stack. So as long as you discover this, it's actually quite easy to run the exploit. Okay. So the hard part is you need to dump the firmware. Sometimes it's not easy to dump the firmware. So we are working on a project and we don't know how to dump the firmware, right? We want to dump that and we want to analyze the vulnerability there. So this is what happens. So this is kind of like a format string at T, but this will be expanded to, everyone will expand to a timestamp like this. Then it will be able to override the save the PC. In this architecture, I think it's not x86, it's different architecture. Also save the registers, and then you can take control. Yeah.
So learning copy like fixed overlay in the previous example.
Yes. So the vulnerability, so like you have been saying vulnerabilities like fgets, right? Yeah. So fgets itself, you can consider it's relatively secure because you specify how many bytes you should get from the input. But how many bytes? That is hard-coded. That's wrong. That's already too big. So memory copy in this case, you are still copying too much.
Does it use the 192?
No, but here, I think this is actually in a loop. See, this is for each T, you're going to do this. Yes, for each T, you're going to do this. Yes. And you say how many are copying here? Here is like already 24 or something. So this is a part you are expanding and the timestamp. And every time it's 8. And yeah. Yeah. So there is a loop. So I think those guys demonstrated this vulnerability in this Hunt-to-Own Automobile 2024. I think they are on this list, but you can see that the first team, they actually took away 300K that weekend by hacking automobile vulnerabilities. There are other teams. Yeah, this guy probably find $1 or $2 and took away 40K. And the bugs they find here, you can see, it's not that fancy, right? It's a simple bug, and it's easy to exploit. All of you are able to exploit those bugs right now. Okay, so that's 40K, 60K there to grab. Okay, so next, let's talk a little bit about how to find buffer overflow in source code, what approaches we have been using, what we have tried, and right now, what is the hottest area. So the first approach everyone can think of is to do some lexical static analysis, right? For example, now we know you're not supposed to use gets. Maybe you are not even supposed to use fgets, right? Definitely should not use string copy. You should use string uncopy, right? Then we can do a source code search, or a fancy way we call it a lexical analysis. We search if you are using string copy. If you say someone is using string copy, you think about if I can exploit this, right? Then you can find many bugs. However, most of code right now, but you say that even some embedded systems, they are still using dangerous function. But most of the applications at the desktop servers we are running right now, the compiler will tell you do not use those functions. Compiler will tell you first to give you a warning. If you there is a compiler option to turn all warnings into errors, then you will not be able to use that, right? Compiler. So the compiler will actually do a semantic analysis to analyze if you are using those functions, not just not a lexical search. However, that's why today I showed you another example, the array example, in which we're not using those dangerous functions, but your program is still vulnerable. The program is still vulnerable because the C programming language allow you to do those kind of things, allow you to use raw pointers to change everything in the address space. That is allowed in the language. Okay, the fundamental issue there. So even if you are not using the dangerous library functions that manipulate those raw pointers, you can still write programs yourself to manipulate the raw pointers to do dangerous things. And the lexical analysis and semantic analysis may not be able to identify those bugs. So that's why a lot of very promising direction and we have been using for 20 or 30 years is dynamic programming analysis. So one of the very good tool in this domain is Valgrind. This is a very good tool. It's open source, super complicated tool to develop, has been there for 20 years. And this can do all kinds of runtime analysis. What it does is for a piece of C code, it will compile that into its own intermediate language, which is called VEX, VEX. Then it will instrument on top of VEX all kinds of security checks. Then we'll run the instrumented program to say if there is an out-of-bound read, if there is an out-of-bound write, many other things. Very, very complicated stuff. Their own VEX language will be compiled into the machine code. So a lot of our dynamic program analysis research was built on top of this tool. It's a great tool. I think several PhD students worked on this. They had their dissertation, several dissertations on this system and tool. We still use this. Another very powerful tool, which was getting a lot of traction in the last 10, 15 years, is fuzzing. Fuzzing can be used together with Valgrind or other tools. So those tools try to instrument the code. Then you run this program in a controlled and monitored environment to say if this program will crash or have weird behaviors. But how do you trigger this program to crash or trigger some weird behaviors? The approach is called fuzzing. So basically, we want to make the software or hardware malfunction. We want to break them with some random inputs. But the random here is not uniformly random in the whole input space. For any program, so for all the programs you have been hacking, so the input space, how big is the input space? For most of them, it's infinite, right? For some of them, they can take a command line argument as input, right? So that is the attack surface. That's the input surface. If you want to talk to the program, you want to feed something into a program, you use a command line. But at the command line, what you can input there? You can input anything. It can be super, super long, arbitrarily long, and it can be short. So if you consider that as an input space, it's actually close to an infinite space, right? But if everything there, everything in that space can trigger a crash, can trigger some weird behavior, not necessarily, right? So that's why you want to find, so for example, you only want to trigger the program to give you a shell. And you wrote a very specific exploit to do that, right? If you just generate random stuff, and feed into the program. So how long does it take to give you back a shell? Right? Maybe millions of years. So in fuzzing, we want to find those areas in this huge input space that can give us crash, give us some interesting behaviors. So that there are a lot of rules to do that, a lot of heuristics to do that. So even though it's called random, it doesn't mean uniformly random in a huge input space. And that's why next semester, I want to have a whole semester to talk about just this. We're going to discuss automatic approaches to find vulnerabilities in C code, binary code, and also other programming language code. There are black box fuzzing or white box fuzzing. There are also other approaches in the middle. So black box fuzzing means you don't really see the internal of the program you are testing or hacking. A white box means you see everything, or gray box, you see something. So one of the very powerful tool for the American body clock, AFL. One of the tool, AFL, fuzzing tool. A lot of fuzzing we're doing right now is because AFL gets very popular. AFL is very effective. Before that, we also talk about fuzzing, but it was not very effective. AFL, which was developed maybe 15, 12 years ago. If you Google AFL fuzzing, you will find that. So that tool uses a new approach. They call it the coverage-based fuzzing, trying to cover more program passes. That's a heuristic it is using. Okay, and to trigger different program passes, you need some information about that program execution. You do not only give it the input and look at its output. That's not enough. That's black box, right? You give input, you say the output. The output could be segmentation fault. So what AFL does is to instrument the program. So to instrument the program, let's consider we have the source code. In other cases, without source code, we can also instrument. A Valgrind can instrument binaries. Let's assume we have source code. AFL will instrument the program. The program will have different branches, right? Like when you disassemble the program in binary ninja, you see different boxes connected together. Each box is called a basic block. In the basic block, the control flow is only sequential. However, at the end of the basic block, it can go to different places. That's why we have different basic blocks. So you will instrument each basic block and collect information at each basic block. The idea is to cover more basic blocks. If you want to find a vulnerability of a piece of code in dynamic analysis, obviously you have to run that piece of code. Right? The piece of code I'm talking about here is at the basic block level. If you do not even run that piece of basic block, how do you find trigger vulnerability here? Try and trigger bugs here, right? So AFL will instrument at the beginning of the basic blocks and randomize the input a little bit here and there and try to cover more basic blocks. And that has been proved to be a very effective way to find vulnerabilities. Then there are coverage-based, mutation-based, grammar-based. Mutation-based, basically, if there is an input that works, that can cover a lot of passes, different basic blocks. We change that input a little bit. We maybe add a letter there. We change a letter, change a byte. Then we put that input, give that input back to the program, and try to. Then the program is highly likely to crash as well, and find a new box. Grammar-based is because some programs, imagine some network protocol programs, like your TCP IP stack. It is taking input from your network card. The input, so what is the input space is quite different from the input space of the programs you have been hacking, like the command line, the file. those network protocols, they are highly structured. We have a format here, right? This byte is the size of this program. This 4 bytes are the checksums. Those 4 bytes are IP address. They have different semantic meanings, right? So for those, there will be programs that will be predicated to check at a very stage of the program whether the input makes sense. For example, if it's a TCP diagram, then there may be a checksum to check if this diagram is valid. If the diagram is not valid, you are not going to reach deeper in the program because the program is not going to pass that, right? So for those, you need to understand the structure of the input, and you can come up with different grammars to describe that. Then we also use symbolic execution, concurrent execution to trigger different branches. Those are also advanced techniques, which has been widely used in the last 15 years. I cannot talk about the details today. If you are interested, take my class next semester. Also for embedded systems, like what we are doing, one of the problem is, let's say after we dump the firmware, we can do static analysis. We can disassemble that, try to find vulnerabilities. And we can also use dynamic approaches to automatically find vulnerabilities. And when we say dynamic, means we need to run this firmware. We run this firmware. But for those firmware, they do not run on our computers. Our computer is x86 or ARM-based. Those run on different architectures. So how do you run on our computer? You have to run on an emulator, right? So that is called rehosting. There are many issues with rehosting. First of all, you may have an emulator. You can use QEMU or whatever, but QEMU doesn't emulate all the peripherals. Those embedded systems, they connect to different peripherals. And they take input from peripherals. If you cannot emulate this part, then the code that is taking input, passing the input from the peripherals may never be triggered. Then you can never find the bugs, right? So how do you solve those issues? So that's rehosting. Also, AI and large language models are playing a more important role here. So right now, there is a DARPA competition called AIXCC. So this is a DARPA challenge. This is an open challenge. Right now, they are already in the semi-final or final stage. So I think there are 10 teams or 9 teams. So those are the teams. Those are 7 teams. 7 teams made it to the final stage of this competition. And each team got, I think, $2 million from DARPA to participate in this stage. Yeah. And this competition is about using AI, large language models, to find and exploit vulnerabilities. Actually, the finding vulnerability part, most of teams are, because I'm friends with many teams here, I'm not participating in this. I don't have a team. If I have you guys 2 years ago, we probably will be there. But yeah, so most of teams, I talked to at least 4 teams already there. So finding vulnerabilities, they're still using flooding. But the flooding part, the safe generation, some teams are using the help of large language models, LLM. Then after the find the vulnerabilities, they also need to patch the vulnerability, fix the vulnerability. And that part, most teams are using large language models to do that. That's why I told you that I have a project that to use large language model to hack the challenges in our class, right? I think I would like to invite some of you, or if you are interested in working on that. So, because right now the student who was leading that project, he just he doesn't want to continue his PhD program. He's leaving for a job. So if any of you, or several of you, wants to work on that, let me know. Then we can keep move forward with that project. So the student actually already finished maybe I would say 60% of the project. He did a fantastic work there, but he doesn't want to move to Boston. He wants to just find a job. And especially after this class, right now you are halfway. After this class, you know all the challenges. You know how to manually hack them. Then we are trying to teach large language models to hack them. We are going to use large language models. So the way we are using large language models, more like using them as agents. I don't know how many of you heard about the concept of agent. You heard about that, right? Large language model agent. So LLM agent. Let's say, so NVIDIA has a post about what large language model agent is. So our idea is similar to this. We are going to use large language model, teach large language model to use tools to hack. Not necessarily just, for example, we feed the binary code to large language model and write prompts, say, give me the exploit for that. Yeah, large language model is not there yet. But we can, kind of like in this class, how I teach you guys how to hack. We use the same approach to teach large language models. We tell large language model, this is a binary, and there is a tool called file, which tells you what binary this is. There is a tool called objdump or ghidra that can give you the disassembly of this binary. From the disassembly, you can look for this kind of vulnerabilities. Then large language model agent will use those tools and step by step, eventually generate the exploit. For example, you did a challenge that you need to override two local variables, but what you get is the product of those two local variables, right? Then you need to get the factors of those two prime numbers, basically. So for that, what we did is we go to the large language model agent. You can disassemble this, and you realize that's a number, and you need to get the primes for that. Then we tell large language model there is a Wolfram API can defactor this, and it calls that API to get that, eventually get the exploit. So we want to do this for all the challenges in this class. I think many teams has been doing things similar, but we started early, so we can still publish a good paper. So if any of you are interested, just let me know. Yeah, we keep going with there. So that's basically the research directions in this area. And we are, my team are moving forward in many of those fronts. And if you guys want to work on this, let me know. We can work together. I really want you guys to sign up for my class next semester. So I think we can just some coursework. We can some course project. We can publish several papers together. We can develop some interesting systems, open source. And if you find the vulnerabilities or find the real zero-day vulnerabilities, you can even get paid. Okay, so that's what I have for today's lecturing part, actually. Then I will talk about the homework. For those who didn't solve all the challenges, you can spend time now on solving those challenges. And the homework this week is actually quite simple. It's only the bypass cutlery part. There will be some bonus points. So if you just follow what I did in class, then you can finish this part, okay, it takes maybe, I don't know, maybe 20 minutes to do that. But if you write an automated script, fully automated, then you get a bonus points. So the idea is very simple. So in the class, I use two terminals. On one terminal, I say what's going on the second terminal, running our exploit, right? So our exploit is not taking input from the first terminal, which has an output, right? So if yours exploit can read the output from the program, then identify if the query is guessed correctly, right? Then you can make this automated. Okay. I don't want to give you the code of that, so yeah, if you run that part code, you get bonus points. Cool. And then maybe you guys can get started, especially for those who didn't solve all the challenges. I will be work around. I will upload the other homework, which is basically the redo the midterm part. So So both homework 6 and homework 7 are due next Tuesday. At the same time.
Yeah, I'm working on that. Uh, three. I think think the last one I'm pretty close. Yeah, I'm pretty close.
Oh, which one is it?
I can know some back. I feel like I can play
Very close.
replay that 92 the act to act and I will catch the flag. And then my any word. It's pretty close. I try it and work. Yeah, that replay the two and
Yeah.
here the finger.
Well,
I don't have enough time to do it. Yeah.
So you cancel that later.
I already kept.
Yeah. We don't have a number yet. No. It's fine. I don't know when we will be on. Sounds like a very fun. For example, the real one, in which part of the order the one you want then we take place and like